Okay. And we're going to go over any questions that you might have from your review.
Okay.
13? Yep. Okay. 13. 1-3. The indicator methyl red has a Ka value equal to 4.00 times 10 to the negative 6. If a 1 times 10 to the negative 3 molar solution of the indicator is used, what will be the concentration of H3O plus at the end point? And that's where the color is orange. What else do we know where the color is orange, intermediate between red and yellow? That is also known as the H3O plus at the transition point. And what do we know about H3O plus at the transition point? It's equal to Ka. Did this concentration of the solution matter at all? Nope. Answer is B. Hi. Oh, I just needed to rant, but I ranted them instead. But you can ask them how good of a rant was it? 10 out of 10. Just about how there's no standards, like in terms of nothing. You can just write things whenever you want to. Anytime. Yeah. And then you graduate, and then you're like, screw that. Nope, life happens. Like what hard? Right? Yes. Yes. Okay. Yeah. See, if I found Miss Belia, I could have ranted at her, and then you wouldn't have had me rant at you, but it's okay. All right. Pardon me? Yeah, I was looking for her, but she was not in her room. Yeah. I'm like, oh, I have 5 minutes. I can go have a good rant, but she wasn't there. Oh, well. Okay, what are we up to next? 36. All right. All right, we have a titration. We have NaOH. You'll notice that there is one OH in this formula. We have H2SO4. You'll notice there are two H's in that. That means this is not going to be one-to-one stoichiometry. So I'm going to write the whole equation, but what you can do is you can, if you want to, just write the reactants, because you don't care about the products for the titration, really. Especially for multiple choice, because you don't need to really show your work. And you can say, I have 2 hydrogens, therefore I need to have 2 hydroxides. Therefore, I have a 2-to-1 ratio. Now, if you're like, I don't know, that seems too complicated, Ms. Spence, you can be like, okay, I'm going to combine my outside ions, Na+, SO4, 2-, that'll give you Na2, SO4. And then, of course, we have water, H2O. Oh, I forgot the H. I made the 2 big. Oh, dear. H2O. And if you have 2 hydrogens, you need 2 hydroxides, which means you will get 2 waters. Like I said, though, for multiple choice, you do not need the entire equation. All you need is the 2-to-1 there. And so you can say we have 20 milliliters of, what does of mean? Times 0.50 moles per liter. Oh. Now I'm going to work in millimoles here. If you hate it, you can work in liters. 20 times 0.5. Oh, I know that. That's 10. 10 millimoles, and that is of the NaOH. Now I know that there is one H2SO4 for every 2 NaOH. So that gives me 5 millimoles of H2SO4. So the concentration then of the H2SO4, I need moles over liters. So if I've been working in millimoles, I need to put my millimoles over my milliliters. So I have 5 millimoles over 30 milliliters of H2SO4. So 5 divided by 30 is 0.167. Oh, thank God, it's the first one. I was like, maybe it's not there. $19, absolutely. Okay. Which of the following set shows the order of increasing pH of the 3 salts? So what we're looking for is we're looking for the ions that hydrolyze because we've got the salts. So those are, we're just going to look at A to start with. We have NH4 will hydrolyze, SO4 will hydrolyze, and CO3 will hydrolyze. So we want in order of increasing pH. So this one is going to be the lowest because NH4 is an acid. So we'll get acidic hydrolysis. So that's in the right position. So really, we're either dealing with A or D. Okay, so we're not looking at C or B. Now we need to ask ourselves, SO4 and CO3 2-, which of those is more basic? Because the one that is more basic will have the highest pH. Yes? So the most basic one will have the highest pH. So let's go look at our data pages. Oh, and look, I did this just with my other class, so I've even got them highlighted. So CO3 2- is quite a strong base. So it will have a very high pH compared with SO4, which is a fairly weak base. So it will produce less hydroxide, so it will have a lower pH. And you can actually prove that. We've got the Kb is approximately 12 because the Ka of the conjugate acid is 10 to the negative 2. The Kb of this one down here, the CO3, it's got a much higher Kb, so it's a much stronger weak base. Okay, so we go back here. And oh, look at this. This is what I wrote for my other block. I went back to the wrong block, but we have the highest because this is a stronger, CO3 2- is a stronger base, and SO4 is a weaker base, so our answer is A. Yes, 20. All right. What is the pH of the solution that results when we mix 100 milliliters of 0.05 molar NaOH? So 100 times 0.05 is 5. So we have 5 millimoles of NaOH. I'm going to show you how to do this faster in just a moment, okay? And then you can say, I have 200 milliliters of 0.025 molar HCl. So 200 times 0.025 0.25 is 5 millimoles of HCl. So, cool thing here is that you have the same moles of acid and the same moles of base. So what do? They neutralize completely. NaOH is a strong base. HCl is a strong acid. The moles equal the moles. What point are we at? We are at the equivalence point. They are all used up. And if they're all used up, and the salt we make is NaCl, what is the pH? 7. Now, if you happen to be good with your mental math, you might notice that the volume doubled and the concentration halved, which means that you know the moles are the same. You don't even have to calculate moles. You say moles are the same. Strong acid, strong base, 7. So you can, if you pick up on that kind of thing, do that question very quickly. But you can also do the calculations. Okay? Any others? 64. Oh, you guys are missing out. In my other class, I sang a song. There's a Beatles song called When I'm 64, but it goes on for quite a long time before it actually gets to the 64 point. So I'm not going to sing it again. You'll have to watch the other class's video should you want to partake of that joyous occasion. Okay. Here we have 25 milliliters of HCl was titrated with 0.5 molar NaOH. We have successive readings. Do you guys know what successive means? Pardon me? No. Successive means one reading succeeds the other. So it means one after the other. Okay? So successive means one after the other, which helps you understand what's going on. So what it means is that these aren't like different trials, and you're not going to take an average. This is like one trial, and when you get to 16.35, you stop the titration and you look at the solution and you say, oh, it is yellow, and you write down yellow. And you add another 0.5 milliliters. Oh, it's 0.4 now, and it is still yellow. All right, and then you add another 0.05, and oh, what color is it? It is now green, and then another 0.05, and it is blue. So where is the equivalence volume? Where's the volume needed to get to the equivalence point? 16.45. Yeah? So that is our volume of NaOH equals 16.45 milliliters. We want to know the original concentration of the HCl. You guys okay if I work in millimoles? Okay, so we have 16.45 milliliters. So the millimoles of NaOH is 16.45 milliliters. And the concentration of the NaOH is 0.45. Moles per liter. So 16.45 times 0.45 equals 7.4 millimoles. Now you have NaOH reacting with HCl. Is this a 1-to-1 or a 1-to-2? This is a 1-to-1 because you've got one OH and one H. So the millimoles of HCl are also 7.4 millimoles. The concentration of the HCl is the moles divided by the liters, but we have millimoles, so we will need to divide by milliliters. So milliliters of HCl is 25, so we have 7.4 millimoles divided by 25 milliliters, 0.2961. You can look it up. It's a song by the Beatles. It's called When I'm 64. Good song. Very catchy. Very singable. Yes? 61? Yep. Okay, a student uses several indicators to determine the pH of a solution and obtains the following data. The pH of the solution is, okay, so we have thymol blue is yellow. Thymol blue is yellow between 2.8 and 8. That doesn't narrow it down very much. Okay, methyl orange is yellow. This is easier if you have your data table right beside you, right? And you don't have to keep flipping back and forth. Methyl, was that methyl orange? Methyl orange is yellow. Methyl orange, that's above pH 4.4. So greater than 4.4. So now we're somewhere between 4.4 and 8.0. Methyl red is red. Keep going to the wrong one. Methyl red is red. So it's going to be less than 4.8. Ooh, I think we might have hit something here. We might not have to keep going. Methyl red is pH is less than 4.8. So I know that it's somewhere between 4.4 and 4.8. So that would be 4.6. I don't even need to look at phenol red or phenolphthalein because, yes.
It used to be below 4.8 for the methyl red to be red.
Isn't that what it says? Yeah.
No, it's like 4.9.
If it's 4.9, it's orange. Yeah. If it's between these two, it's orange. Yes. What if it's 4.8? I'm not going to ask you that because that's a stupid question. Do you know what I mean? Your question is not stupid. That would be a stupid question for me to ask you. You know what I mean? Your question is not stupid. I want to be clear on that. It would just be cruel and heartless to be like, here we are at the end of the range. What's the color? I'm just doing it to trick you. That would be evil, you know? So I'm not going to do that. Yeah. All right, what's next? Yes. You consider both, yes, because it is one substance. It's diprotic. So you have H2TB, and that form is red. And then it dissociates. Its first dissociation, it turns yellow. And then the second dissociation, it turns blue. Yeah? Yeah. Written 8, yes. Oh yeah, omit 8. You don't know those. So there we are. And 12. No, 12 was, I did say to omit 12. So 12 is also omitted. That's why you don't know them, because they were in section 5.7. Yeah. Five in the written, yes, absolutely. Okay, so we want the mass of NaOH that would need to be added to 10 milliliters of 2 molar HNO3 to obtain a pH of 1.0. So this is our concentration of HNO3 initial. And we want to have a pH of 1.0, which means this is our final. So that means the concentration of H plus final, we want to be equal to 10 to the -1, which is 0.1. Okay, so that's 0.10 molar, and that is equal to, because HNO3 is a strong acid, that's also the H plus final is going to be equal to the concentration of HNO3 final. Okay, now we can do a RICFA table if you would like, or we can just do numbers if you would like. Do you have a preference? No? Okay. Why don't we do a RICFA table just because it keeps you organized? Yes? So we know that HNO3, we are going to react it with NaOH, and we don't know how many grams. So we have HNO3, and we're reacting that with NaOH. They react 1 to 1. And we can calculate the millimoles of HNO3 initial, yes, because we know that initially we have 10 milliliters of 2 molar, yes? So millimoles of HNO3 initial, 10 milliliters times 2 moles. Stop making noise. No. Stop making noise. There you go. 2 moles per liter gives us 20 millimoles. Okay, so we have 20 millimoles. What do we want for our final? Well, we're still going to have 10 milliliters because we're adding a solid, yes? So the volume won't change, at least not significantly. So we're still going to have 10 milliliters, but our concentration now is going to be 0.1 molar. So our millimoles of HNO3 final, 10 milliliters, times 0.10 moles per liter is equal to 1 millimole. So how much do we need to react? We need to react 19 millimoles, which means how much NaOH did we need? 19 millimoles minus 19 millimoles, and that gives us 0 millimoles. So we need to know the mass that contains 19 millimoles. So we're going to say 19 millimoles is equal to 19 times 10 to the negative 3 moles. That's the fastest way I find to do it. Or you can just move the decimal place and you can say that's equal to 0.019 moles. Either way, and then you'll multiply it by the molar mass of NaOH, which is 40 grams per 1 mole. .76. And then I would go back and look at all of my sig figs and say, whoa, I hate it when it does that. Okay, where'd it go? There it is. Okay. I have 2 sig figs here, which gives me 2 sig figs here, which gives me 1.0. That gives me 20.0. So 20.0 minus 1.0 is 19.0, so that's 3 sig figs, so 0.760 grams. That is number 4. 5. Well, it's the second number 4. $21 multiple choice and Laura. Number 3 written. Okay, so I'm going to just put over here 21 multiple choice. We'll do 3 written while we're here because it's close. Stop jumping around. Okay, so we have 79.8 milliliters of 0.18 moles per liter of HNO3. So that is equal to 79.8 times 0.18 is equal to 14.364 millimoles, but I'm going to change it to moles because my grams is going to give me moles. So I'm going to move my decimal place 3 places, 0.0144 millimoles. Don't round off here though, just keep that number in your calculator. Okay, so that's how many millimoles of HNO3 we have. We have 3.75 grams of RBOH. And the molar mass of RBOH, rubidium, is 85.5 plus 16 plus 1 is 102.5 grams per mole. So 102.5 grams per 1 mole. .0.03658 moles. Oh, that's not millimoles, that's moles. Okay. Or I could make this one into millimoles, which would be nicer, wouldn't it? They're nicer numbers. What do you guys want to do? Moles or millimoles? Moles? Okay. So now we have HNO3 plus RBOH. What's the ratio going to be between those two? 1 to 1, 2 to 1, 1 to 2. What's it going to be? 1 to 1 because we have one H and one OH. Because this is a written response, I would probably write the products RbNO3 plus H2O. And I'm going to do a RICFA table to figure out how many moles I have left over at the end. So I have 0.014364, and this is millimoles. And I have 0.036585 no, that's not millimoles, it's just regular moles, sorry. Who's going to get all used up? HNO3, so minus 0.014364 minus 0.034164. That equals 0. Nope. 0.1436. Oh, I transposed my digits all over the place. 0.014364. There we go. That's better. Minus 0.014364 equals 0.02221 moles of RbOH is left over. And we wanted the concentration, we wanted the pH of the solution. So what is our volume? 79.8 milliliters. So the concentration then of the RbOH is equal to the concentration of OH minus, because they're 1-to-1, which is 0.02221 moles divided by our volume, which was 0.0798 liters. You can save yourselves all these zeros by doing it in millimoles, but it's up to you. Divided by 0.0798 equals 0.27846 molar OH minus. POH, negative log, 0.2785. .5552 pH equals 14. I'm just going to put a bunch of zeros in there. Minus 0.5552 equals 13.4448. How many sig figs do I have? That was ugly. Okay. 3 sig figs, 3 sig figs, 3 sig figs, 2 sig figs. 0.18 what? Oh, 0.18 molar. Yeah, 2 sig figs. Okay, 2 sig figs. So that's going to be 13.44. That was tiring. 41? The first one from the written? Oh, multiple choice, yes. And did I lose track of your multiple choice along the way? Oh, it was yours. And I did. 21 multiple choice. So we want 21 and number 1. Yes? Okay, we'll hit 21 and then we'll do number 1. 21. Okay. So there's 2 ways of doing this question. You can find the moles of each thing. You can do the Ricfa table, yada, yada, yada. There's a quicker way of doing it because they are both the same concentration and it is monoprotic and monohydroxic. So the quick way to do this one is to say I have completely neutralized 20 milliliters of the HNO3. So all of the HNO3 is neutralized. And because they are the same concentration, I can do this and I can say 20 milliliters of the KOH is neutralized. Which means that I have 30 milliliters of the KOH, which is not neutralized. And then I can just do a dilution, right? Because I have 30 milliliters not neutralized in a final volume of 70 milliliters. So I can say I have 0.2 molar KOH times 30 divided by 50, or sorry, 70. That's the fast way to do it. If you don't like that, you can say how many moles of HNO3 do I have? I have 20 milliliters times 0.2 molar HNO3 is 4 millimoles of HNO3. I have 50 milliliters of 0.2 molar KOH, which is 10 millimoles of KOH. So I have 6 millimoles of KOH in excess. Yes, you don't have to draw the whole RCVA table. You can just be like, okay, I'm using up all 4 millimoles of the HNO3 and I'm using up 4 millimoles of the KOH. So I have 6 millimoles of KOH left, and that is 6 millimoles in 70 milliliters. And you'll get the same number as you do here, which is, I don't know what, 6 divided by 70. 0.0857. Did it want pH? Yeah, pH. Okay, so that was the concentration of OH. That's the concentration of OH. And so the pOH, 1.07, and the pH is 12.9. Ooh, 12.93. There we go. But if you can wrap your head around that whole, like, I've neutralized 20 milliliters, and so I have 30 milliliters left over, and now I'm just diluting that 30 milliliters, that's a really fast way to do questions like that in a multiple choice section. Yeah. Oh, the first one. Yes, thank you for reminding me. Okay, the acid form of an indicator. So do we want HIN or do we want IN minus? Which is the acid form of an indicator? HIN. So we want either this one or this one reacting in a basic solution. Base. Done. B. Yes? So we have a basic solution, which means we're going to have hydroxide, and we have the acid form of the indicator, And that's it.
$106.
106. Sure thing. Which of the following is best for preparing a buffer solution that works in basic conditions? So you have a choice of using a weak acid plus the salt of the conjugate base, Wascaba, or a weak base plus the salt of the conjugate acid, Wubska. So here we have a weak acid and we have the salt of the conjugate base. Here we have a weak base and we have the salt of the conjugate acid. NH3 is a weak base and NH4OH is a strong base. Oh, that's sad. And over here we have a weak acid, whoops. And the salt of its conjugate base. Even if you didn't know how this worked, could you, by process of elimination, choose the correct one? Could it be A or C? Why or why not? Yeah, we don't have a weak base, okay? Well, we do have the conjugate. These are conjugate weak bases. This is the salt of the conjugate weak base. So we have weak acid, weak base, weak acid, weak base, salt of the conjugate weak acid. Even if I didn't know, I would say these two are the same, weak acid and salt of the conjugate base. You can't have both of them be correct, therefore you can eliminate them. Yes? Pardon me? Doesn't matter. It's a weak acid plus the salt of a conjugate base. From the information you have in the question, those are essentially the same answer. Yeah? The grade 12 answer to this, not the university answer, the grade 12 answer to this is that if you want a basic buffer, you want a weak base plus the salt of the conjugate acid. That one. If you want an acidic buffer, to buffer below pH 7, you want a weak acid plus the salt of the conjugate base. Yeah. Pardon me? 107. All right. So we have, okay. So we have a buffer containing CH3COOH, CH3COOH, and it contains NaCH3COO minus. Okay. And it has a pH of 4.74. Now we're going to add some HCl. Oh, we have 1 molar and 1 molar and 1 liter. So I have 1 mole of this right now, and I have 1 mole of this. And I add 0.2 moles of H+, which means it shifts to the left. Okay, which means that this is going to become 1.2 moles, yes? And this is going to become 0.8 moles. My hydrogen ion concentration is going to go up, right? And it's going to go back down, but it's still going to be higher than it was before, which means my pH is going to be slightly lower. Have we overwhelmed our buffer here? Have we used up all of one of the ingredients? No, so we're not going to see a drastic change in pH. So we need the pH to go lower, but not drastically lower. pH 4.56. Yeah. 105? Mm-hmm. The salt produced by neutralization reaction here. Oh, here. Ah! Oh, this is a good one. I like this one. Oh, yeah. All right. So we see we have NaOH. What kind of an acid are we titrating? We are titrating a weak acid. How can you tell it's a weak acid? We have a hill. We have the equivalence point at pH 8.7. Yes? So right at this point, HA plus NaOH goes to H2O plus NaA. And we want to know about this salt here. What is it doing? Is it undergoing acidic hydrolysis, basic hydrolysis, or no hydrolysis, or both hydrolysis? Does Na undergo hydrolysis? No, but A minus, it's the conjugate base of a weak acid, so yes, it will. So A minus will undergo hydrolysis. You could also just look and say, oh, it must be basic hydrolysis because my pH at the equivalence point is basic. Yeah? But you could also say, okay, well, if this undergoes hydrolysis, it will become HA plus OH minus. Oh, look, basic. Yes. 103. Suggest a suitable indicator for this titration. So we are at pH 8.7. And the vertical section is approximately from here to here. So we want something that changes at about 8.7. I would say that one looks pretty good. So either thymol blue or phenolphthalein. Yeah, you just want the value in the middle to be close to 8.7. So either of those would do nicely, okay? I would choose phenolphthalein just because it's easier to see, colorless to very slight pink, than to decide what shade of green is the greeniest green that you have ever seen, okay? Yes? 104? 102. 102, 102, 102. There we go. If the NaOH solution is in the burette, the solution in the beaker is most likely, well, we have a base here, so it needs to be an acid. We have base, acid, acid. And we see that there is the hill. We see that there is the pH at the equivalence point is greater than 7. And so it is most likely a weak acid. Well, it has to be a weak acid, and that one's weak. This one is strong. It would start lower and it would go like this. Yeah? If it were a strong acid. Yeah? So it has to be a weak acid because we have that hill and we have the pH at the equivalence point greater than 7. Yeah. 55. Okay, we have, oh my gosh, it's almost the same question. We're just adding KOH instead of HCl this time. So we have CH3, COOH in equilibrium with H plus and CH3, COO minus. And we have 1 molar, 1 liter, 1 molar, 1 liter. So we have 1 mole of this stuff and we have 1 mole of that stuff. And we are adding 0.2 moles of OH minus. 0.2 moles of KOH is essentially 0.2 moles of OH minus. When we add OH minus, that will cause water to form, which will shift the equilibrium to the right. So what that means is that my concentration of my concentration of hydrogen goes down, but then as we shift to the right, it goes back up and it finishes below, so it is slightly lower. Which means, what about the pH? The pH will be slightly higher. Now, we have 2 choices for slightly higher. We're starting at pH 4.74. We could go up to 4.75, or we could go up to 4.92. Have we added a substantial amount of base compared with our acid, or have we added an insubstantial amount? 0.2 is 1/5 of 1. That's fairly substantial, yes? So we're not going to have a teeny tiny change in pH. We're going to have a small but meaningful change in pH. Because we have added a meaningful amount of OH, not a negligible amount of OH. So the answer is going to be C. $46. Okay, what volume of HCl solution is needed to neutralize? I'm going to just call this 0.2 liters because that's a nasty number. And that is 0.01 molar LiOH. So whenever I'm doing a neutralization, I'm usually looking at moles. Who can I find the moles of? The LiOH. So my moles of LiOH is equal to 0.2 liters times 0.01 moles per liter, which gives us 0.002 moles of LiOH. LiOH and HCl Do they react in a 1-to-1 fashion or a 2-to-1 fashion? 1-to-1 because there's no 2's in there. So my moles of HCl is also equal to 0.002 moles. If you know moles and molarity, can you find volume? Yes. So you will then say, okay, my volume of HCl is equal to that many moles. I want to cancel my moles and find my liters. And that will be 4 times 10 to the negative 2, which is 0.04 moles per liter. So that's 5 times 10 to the negative 2 liters. I think the answer is A. Yep. Yeah. 54. Indicator, propyl red, we add NaOH. So the OH reacts with the H3O plus. That causes the H3O plus concentration to go down, which will cause this equilibrium to shift to the right. So it shifts to the right. And if it's shifting to the right, we have two choices. We have HPR increasing, which is not true. I don't like the word as here. I would say because H3O plus decreases, but it's the best answer out of the ones that they've given us, so I would go with that. It might be a little confusing because of the as, but as in that context can mean because. Yes. Yeah, OH minus, H3O plus, that gives you 2 waters. So this hydrogen, one of these hydrogens, that leaves you with an H2O, right? Because it lost a hydrogen. And then this one gained a hydrogen, so now we have HOH, which is another H2O. So it's the same neutralization as H plus and OH minus, it's just fancier. Okay, yeah. How are we doing? We got more questions? 47, yes, we sure can. Oh, diprotic acid. What am I going to call it? I'm going to call it H2A. And it's reacting with NaOH. This is multiple choice, so I do not need to write out the entire equation. Is that going to be a 1-to-1 ratio or a 2-to-1 ratio? 2-to-1, because we need to have 2 hydroxides to neutralize the 2 H's. Now, we have 4.5 times 10 to the minus 3 moles of NaOH. We need to figure out how many moles of the diprotic acid we have, because we want to find the mass of 1 mole, which is the molar mass, yes? And molar mass is equal to grams over moles. We know the grams of the acid, so that's going to be easy to plug in right here. We need the moles, the grams of the acid over the moles of the acid. Right now we have moles of base. Yes? So we need to convert moles of base into moles of acid. So we need to look at our coefficients there and say we have 1 mole of H2A for every 2 moles of NaOH. So that's going to be 2.25 times 10 to the negative 3 moles of H2A. So now we know that the grams are 0.45 moles. That's in the question. We have found 2.25 times 10 to the negative 3 moles. We do the division, 0.45 divided by 2.25 e negative 3 equals 200. And that is grams per mole. So that's grams per 1 mole. Yeah? Yeah. Sorry? 96. A solution is yellow when orange 4. So orange 4 is yellow. And Brom Cresol green is also yellow. So let's go check out orange 4 is yellow above pH 2.8. So the pH has to be greater than 2.8. Brom Cresol green is yellow. Where's Brom Cresol green? There it is. Brom Cresol green is yellow, which means that the pH is less than 3.8. So we are somewhere between 2.8 and 3.8. So that's going to be 3.2. Yes? That's not really why. No, you just have to look at the 2 and say, is it greater than this or is it less than this? So in order for, Ethan's not here, sorry.
Oh, not here?
Not here.
Okay.
Never here. Okay, yeah. Thank you. So orange 4 is going to be 1.4 to 2.8 red to yellow. Okay, 1.4 to 2.8 red to yellow. 1.4, 2.8. Orange 4 is red. It is yellow. And it is orange. Okay? So in order for orange 4 to be yellow, we have to be higher than 2.8. Yeah? Now, Brom Cresol green, I'm just going to call it BCG, changes at 3.8 to 5.4 yellow to blue. 3.8 5.4 yellow to blue. So below 3.8 it is yellow, above 5.4 it is blue, and in between the two it is green. The only place where those overlap The only place where they are both yellow is in between pH 2.8 and 3.8. So somewhere in there. It could be anything in there. It could be 2.9, it could be 3.4. Yeah, just whatever the question happens to give you. Yeah. Yes. Number 9. Oh, number 9, there's a problem with the question. Just omit it. Well, we could try it. There is also a problem with the question, though, with the answers.
But also, we should have to know, like, questions like 73. Yeah, look at it.
Okay. Yeah. What is 73 about?
What is the common source of ethanol?
Didn't I say to omit that one? Yeah. Yeah, it was on the list of omitted questions. The list of omitted questions is in the review, omit multiple choice number 2, 40, 63, 73, 92, written response number 7, 11, and there might be one more in the written response that I can't remember.
Sorry for the interruption. Would all students who have applied for a
Yep.
program, they stop by the career.
It's in upcoming quizzes and tests. It tells you which ones to omit.
Apply for a district program. Thank you.
Have you, pardon me? I have a meeting after school today. Oh, by the way, I am here at Flex tomorrow. I thought I wasn't going to be, but I am. I'm not here Flex on Wednesday.
Question.
Yes,
79
79.
or 71. Nursing.
Did you take into account that there's a 2-to-1 ratio? Because you have 2 hydrogens to 1 hydroxide?
Oh, it's 2 to 1.
Uh-huh. And probably the same thing here, 2 hydroxides with the HCl. So you need to write the reactants and get the stoichiometry.
Okay.
Yeah? Yeah. Oh, you can omit number 12 as well. And 8. 12 and 8.
Don't do it.
What? Oh, just let me write this down before I forget. And 8 and 12. And you have books for me. So exciting. Okay. You know what I'm going to do? I have to go because I have a meeting. So I'm just going to put your name on them on a sticky note for right now. Okay. Ruth.
Thank you.
Thank you.
Thank you.
Thank you very much.
Sometime this week.
Awesome. That's great.
See you.
I just wanted to return to the practice that I never did. Yeah, just one of them.
Oh, yeah. Thank you.
No worries, thank you. That like the content file was okay, but the timing could be a little bit better.
Yeah.
Yeah, but that's
That's life, right? Yeah. Yeah. Okay. 3:05. All right. Whoa. Blinding.